So we are week 8, lesson 2. We're going to continue our discussion about stereochemistry regarding alkenes. If you remember, we left off in lesson 1 talking about the cis-trans relationship. Again, we brought that up when we had cycloalkanes, and now we see that they can be present whenever you have alkenes. But also, we have some special terms, designations, I guess, for when you have 3 or 4 substituents. Cis and trans was when you had 2 non-hydrogen groups on an alkene, okay, on different carbons. They can either be on the same side or opposite sides. Well, what do you call it when there's more than 2 groups, like 3 groups or 4 groups? Okay, so a tri or tetra substituted alkene. Well, we have this thing called the E or Z designation, so we'll explain what that is. So the good news is the rules that we need to apply you've already learned, because we use the same Kahn-Ingold prelog rules that we talked about back with our discussion on chiral centers. Remember, you rank them according to their priority. Okay, it's the same set of rules for this. So what you're going to do is you're going to rank the 2 groups according to the Kahn-Ingold prelog rules for each carbon. Okay, and then you just need to decide which of those 2 is higher priority and which one is lower priority. But the key thing is to remember to do it for each carbon. All right, so if you don't remember the rules, here's just a quick refresher. So the bottom line is you rank according to atomic number. So you rank them according to atomic number. The higher the atomic number, the higher the priority. And if the first atom doesn't make the decision, then you move on to the next connected atom and the atoms that it's connected to, and then the next connected atom and the atoms it's connected to, and so forth and so on. So rule 1 and 2 there, you can see we just apply the atomic number, the ranking according to the atomic number when appropriate. And then there's that situation many times where you have something with a multiple bond, double bond, triple bond, whatever. And so remember that the situation there is if you have a double bond, that's the multiple bonded atoms are equivalent to the same number of single bonded atoms. So if you don't remember what that means, let me draw an example. So if you have something like, a carbon double bond to an oxygen, a carbonyl group, that's the same thing as like a carbon with 2 oxygen. All right, it's the same thing as that for deciding which one is higher priority. Okay, so that's it. Those are the rules for applying the EZ designation. So then we got to decide, well, what is E and what is Z? Okay, so the Z geometry is when the higher priority groups are on the same side. So the molecules which have higher ranked groups on each carbon are on the same side are what we call Z geometry. Okay, so if you're, well, I'll give you what it means for E, and then we'll give you the little hint to how you remember this. So the E geometry, of course, then is just opposite sides. So molecules which have higher ranked groups on opposite sides. Okay, so the little hint that you can try and remember to is this. It's Z, Zame, Zide. Okay, you pull out your best Arnold Schwarzenegger impression or German accent. Okay, to help you remember that when the higher priority group of each carbon, remember you got to do each carbon. You look at this carbon, you assign one group on the carbon to be higher, the other one is by default lower. You do the same thing on the other carbon. And if both of the higher priority, or you could say, I guess, both of the lower priority are on the same side of that alkene, that's Z geometry. If they are on opposite sides, that's E geometry. Okay, so let me do a couple examples for you here. So we will apply the Kahn-Ingold prelog rules to decide, all right, so here is my alkene right there. And so we'll look at the 2 groups on the left side. All right, so we're going to compare them and which one is going to be higher, which one is going to be lower priority. So the first atom that's attached is carbon either way. There's a carbon there, there's a carbon there. So I can't make my decision based on that. But this carbon up top, that's attached to 3 hydrogens, right? That's a methyl group using the skeletal structure abbreviations, right? That's a carbon attached to 3 hydrogens, whereas this carbon's got attached, it's got 2 attachments to oxygen. So that oxygen tells me that this one is the higher priority group, and that means that this one is the lower priority group. So we do the same thing over on the other side. So what is not shown here is that bond to hydrogen, again, because we've got the skeletal structure drawn. Hydrogens are implied. And so you just compare the atomic numbers here, because this is a chlorine attached to that carbon versus a hydrogen attached to that carbon. Well, chlorine has a higher atomic number, so this one is the higher priority, and this one is the lower priority. So since they are on opposite sides, remember that's E. All right, so moving on to the next one here. So once again, this is the same thing that I just did, right? So we decided that this one was higher. Okay, this one was lower. Okay, well, over here, we've got a carbon. It's attached to 2 hydrogens. Oops, that doesn't even look like a bond to a hydrogen, but that's what it's meant to look like. And then, okay, well, here it's got the bond to the oxygen. So the oxygen is higher atomic number, right? It has a higher atomic number. So that means that this one is higher priority. And this one is the lower priority. So since they're on the same side, the lowers are on the same side, the highers are on the same side, that means this is the Z designated. Okay, so now we're going to talk about some reactions with alkenes, wrap up chapter 7 with the discussion on reactions with alkenes. And so we've already talked about the basic reaction of an alkene with a halo acid, HBr, HCl. And so you have seen this mechanism before, where the double bond acts as the nucleophile. It's attracted to hydrogen, which is the electrophile, and it adds the hydrogen and creates a carbocation, this positively charged carbon, which then is attacked by the bromide, which serves as the nucleophile, to, in a second step, attack that electrophile carbocation to give you a product. Okay, so now we're going to look at, well, how is it different if you start substituting some of these hydrogens with alkyl groups? So instead of 4 hydrogens around the carbon-carbon double bond, what if you start substituting those with alkyl groups? How does that affect the chemistry? Okay, so the first thing that happens is, or let me read this bullet and then we'll move on with the mechanism. So when the alkene has alkyl substituents, the carbocation is formed on the most substituted carbon. Okay, so that's the key. The carbocation is formed on the most substituted carbon. All right, so you can see that in this example here for step 1. So once again, the double bond acts as a nucleophile, attacks that electrophile hydrogen because it's got the partial positive charge. All right, and this carbon in the middle, the carbon in the middle right there, is the most substituted. The carbon over here on the right, it's not substituted at all. It's just got 2 hydrogens. But the carbon here, it's substituted with 1 alkyl group. This methyl group is like a substituent. So it's the most substituted. Okay, so that's where the carbocation is going to form. Now, the consequence of that is that the hydrogen, the pink hydrogen, gets added to this carbon on the right. Okay, and so you can see that right here. It gets added to the carbon on the right. So it still has its octet. It's got its 4 bonds, but the carbon in the middle now is the carbocation. It's got the positive charge. It's just got the 3 bonds. All right, so that's step 1, which is going to go on to react in step 2 with this bromide. The bromide serves as a nucleophile to attack the carbocation in step 2. But before we move on to that, let me, just to make it more clear, show you what's not formed. Okay, so let me change colors here. So what's not formed is this carbon with the 3 hydrogens. Okay, formed with the carbon, and this carbon had 1 hydrogen on it, so I'm going to draw that. And then this carbon had 2 hydrogens over here. Boy, my penmanship is really bad. I apologize, but that's supposed to be a C. But then let me switch colors just to show you where that other hydrogen went. So this is not formed. The hydrogen does not go here in that middle carbon in order to give us the carbocation on that end carbon. Okay, that is not formed. That's not what happens. All right, that would lead to a different product. Okay, so step 2, it's written right here. It's already in your handout there as well, that the nucleophile, which is the bromide, attacks the carbocation, and so you get the halogen attached to that middle carbon. Now, this actually has a name. This happens faithfully all the time. So somebody discovered this and named it after himself. And so his name was Markovnikov. So this is known as Markovnikov's rule. And this is one way to state it. So in the addition of a halo acid like hydrobromic acid, hydrochloric acid to an alkene, the H attaches to the carbon with fewer alkyl substituents, and the X, the halogen, attaches to the carbon with more alkyl substituents. Okay, so again, for example, if we have this alkene right here, the carbon on the left, it's got 2 methyl substituents. It's the most substituted. The carbon on the right has no substituents. It's just got the 2 hydrogens attached to it. So when it attacks, or when it is attacked by a halo acid like HCl, according to Markovnikov's rule, the hydrogen will go on the carbon that's least substituted, and the chlorine will go on the carbon that's most substituted. So you end up with 2-chloro-2-methyl propane, and that's it. That's the product. Okay. However, sometimes you can end up with a mixture of products because it doesn't matter what the alkyl substituents are. So in a situation like this, where you have 2-pentene, okay, each carbon has 1 hydrogen and 1 alkyl substituent. So because of that, you do get a mixture. You end up with, the bromine being added to either carbon number 2 or carbon number 3, ending up with 2-bromopentane or 3-bromopentane. So the point being that it really doesn't matter what the alkyl substituent is. It matters how many alkyl substituents are present on that carbon. Okay, so here's just another way to restate Markovnikov's rule. So in the addition of HX to an alkene, the more highly substituted carbocation forms as the intermediate, rather than the less highly substituted one. So the carbocation that forms is the key. It's forming. The reason why it happens this way is because the carbocation, which is the intermediate, needs to be stable. It's going to be as stable as possible. And so we're going to see in the next couple slides how there's a relationship between the amount of substitution and the stability of that carbocation. Okay, so for example, and this is one I think you have in your handout there, going, the same one that we've already talked through. Okay, so using our curved arrow stuff here, we got this. So the curved arrow is going to attack that hydrogen because it's got the partial positive charge, whereas the chlorine, of course, has the partial negative charge. So that's the first step, and it gets added to the carbon with the least amount of substitution. So that's the one with the CH2. So you got the 2 hydrogens there, you get the 2 hydrogens there. So that's why it adds there. And you get the carbocation formed on the carbon with the most substituents. In this case, it's got both those methyl substituents. Okay. What doesn't happen is you don't add the hydrogen to the highly substituted carbon. So that's why, it's pointed out that this does not happen. This reaction pathway does not occur. You do not add the hydrogen to the highly substituted carbon, and therefore the chlorine end up on the less substituted carbon. So this is not formed. All right, so I think this one, it's just another example, but it's not in your handout. I just want you to pay attention to see if you can kind of pick out what happens on your own, or you understand just by follow along on your own here. So again, what we've got this pi bond acting as a nucleophile to react with the electrophile, the hydrogen, partial positive, partial negative, okay? And it's going to get added to the less substituted carbon. So that's this one right here, because this carbon has 1 hydrogen and 1 alkyl group. So this is a carbon, right? A CH2. This carbon has got connections to 2 other carbons. So this is the more substituted one. This is the less substituted one. So it's going to add to the one that's less substituted, which is reflected right there. Okay. So that means that the carbocation is going to be a tertiary carbocation. Remember that definition of, primary, secondary, and tertiary. That the tertiary, that carbon is attached to 3 other carbons. 1 carbon there, 1 carbon there, 1 carbon there, for a total of 3. That carbon is attached to 3 other carbons, so it's called a tertiary carbocation. And so then it goes on to get attacked by the nucleophile, and you end up with this product. You do not end up with a product on the other side. Okay. All right. So that's called Markovnikov's rule. All right. So let me do another example here. So we want to predict the products of the following reaction. So we have this alkene, and you can see from the structure here that the most substituted carbon is the one that's part of the ring, and the least substituted carbon is the one involved in the CH2 right here. And so if it reacts with a HBr, what's going to happen? Well, let's draw some curved arrows to again just show the mechanism. So this double bond is going to act as a nucleophile, right? It's going to attack that hydrogen because it's got the partial positive charge, acting as the electrophile, and the bromine gets the partial negative charge. And so there is a bond there. It's really small, but I'll try and show it. And so the electrons in that bond between the hydrogen and the bromine are going to move also over to the bromine to get bromide. So that's going to be one of our products. So that pair of electrons moved on to the bromine, forming a bromide ion. Okay. And so now the question is, well, which carbon is this hydrogen going to get attached to? Well, it's going to get attached to the one that's the least substituted, which is that carbon right there. So our carbocation is going to be in the ring. So there's our carbocation right there. This should be a plus sign. Ugh, my penmanship. And then the CH, now it's a CH3 because that hydrogen got attached to that carbon. So now this bromide, I should say, is going to react as a nucleophile with this electrophile, this carbocation, okay, to give us the product of the 1-methyl, 1-bromo. So this has two substituents on it, a CH3 and a bromine. So 1-methyl, 1-bromo cyclohexane. All right, so that's one type of question that's possible. The other type of question is a reverse engineering kind of a situation where you walk it backwards. So this is an example of a backwards Markovnikov problem. So we know the product. We want to go backwards and predict which alkene is required to prepare the following product. And you'll sometimes there's more than one, and that's the situation here. So what I recommend that you do in this situation is, first of all, just go back to the carbocation. So that's kind of step number one. So I want to just kind of go backwards to the carbocation. So go to the carbocation. All right, so I know that one of the products, the nucleophile that attacks the carbocation, was the halogen, so the iodide. So that was one of them. And so what was the carbocation? Well, it was a cyclohexane ring with a CH2CH3 on it, CH2CH3, and the plus charge was on that tertiary carbon at that corner in the ring. Okay, so those are the two reactants for step 2 that went on to produce that product. Okay, so then we just need to think, well, wait a minute. So a hydrogen then either was added to, so where was potentially a hydrogen added to? So now I'm going to change colors to illustrate where those hydrogens could have been added. So it could have been added here in where I've drawn it in the blue, or it could have been added here where I've drawn it in the blue. Okay, because that's just what we have here, that we have. And by the way, this is an equivalent position. So the reason why I'm not, also talking about what's going on in this carbon here is because it's exactly the same as what's going on in the carbon here. They're identical compounds. So that being the case, that means that these were added, these were hydrogens that were added from, in this case, HI. So these hydrogens were added from HI. So that means that I could have had the double bond either right here or right here. Okay, either one of those double bonds would have given me an added hydrogen on one of those carbons and a carbocation right there. Let me change colors again, and I'll show you what that looks like. Nope, draw. Okay, so that is going to look like either we got our 6-membered ring with the CH2, CH3, and the double bond there. Okay, that could have been our original alkene, or it could have been, so there's my 6-membered ring again. And now I could draw the double bond between, so then it would be CH3. Okay, so that means that the hydrogen could have been added to that carbon, or it could have been added to that carbon, either way. And that would lead to these, either way, that would lead to this overall product right here. Okay, so it requires a little bit more brain power, I think, to work backwards. But that does demonstrate that you understand the Markovnikov's rule. So either one of those original alkenes, when reacting with HI, would produce this product right here. All right, so let's take a look at what we got here. I'll talk through it real quick and then show you the prettier answer with the PowerPoint. But the key is recognizing which carbon is highly substituted and which one is less substituted. So this carbon right here has got two substituents on it. It's got the CH3CH2 and it's got the CH3. So it's a methyl and an ethyl substituent. Whereas this carbon right here on the other side of that double bond is just got one substituent on it. It's got the hydrogen, but then it's got this other group right here, the isopropyl group. So because this carbon is more substituted, it's going to be the carbocation. And that means that the hydrogen gets added to the less substituted carbon. So that's where the hydrogen goes. It goes here. And then the carbocation is on the more substituted one. And so then the bromide, which then is the nucleophile in step 2, it reacts with the carbocation. And so the bromine ends up here on that tertiary carbocation, and that's your product. So why is there such thing as Markovnikov's rule? Why does the carbocation form on the most substituted carbon? Why does the hydrogen go on the least substituted carbon? Well, it's because of the stability of the carbocation. And in order to understand that, let's take a step back and remember a few things that we've discussed before, some in Gen Chem, some here. So one thing to note is that carbocations are planar. They are sp2 hybridized. If you need to convince yourselves of that, just think of what we did to come up with that hybridization scheme. You calculate the steric number. The steric number was the number of atoms or groups connected to that central atom plus the number of lone pairs. So in this case, it's the steric number of 3. You got 1, 2, 3 plus 0 lone pairs. So it's a steric number 3. Then you memorize that's trigonal planar, and you memorize that that's sp2 hybridized. Okay, and the other important feature about that, when you know that it's sp2 hybridized, is that you've got that third p orbital that's just vacant, right, ready to receive electrons. And that's kind of the definition of an electrophile, something that's looking for electrons, able to, positive charge, able to receive electrons. So it's perfectly set up for that. So those 6 valence electrons that are present are part of those sigma bonds, and you've got that p orbital that's unoccupied, and it's kind of poking out away from the rest of the molecule, up above and below, so it's just ready to receive electrons from a nucleophile. So then the question becomes, well, what around that carbocation can kind of tone it down a little bit? That positive charge is like screaming, okay? And so what we see is that the more alkyl groups that you substitute on to that carbocation, the more electron density that is present to sort of tone it down, to tamp it down a little bit. So the stability increases as you go from the methyl to a primary to a secondary to a tertiary, which again is shown from inductive effects. We talked about this when we back in week 2 probably, when we talked about the inductive effect on how the strength of an acid, what makes an acid stronger or weaker. One of those structural features was the presence or absence of electronegative elements, right? Because they were electron withdrawing. Well, it's just the opposite here. If you start surrounding that positive charge with alkyl groups, well, that's a lot of electron density that can kind of tone it down. Okay, you start there with that methyl. That's like, I'm positive, I've got to do something about this. It's that bright blue, right? Well, you start putting alkyl groups around it, and that's a lot of electron cloud that can kind of say, all right, don't worry, we've got some electrons for you. Don't worry about it so much. So it tones it down a little bit. So by the time you get to that tertiary carbocation, there's enough electron density around it to, to make it happier, so to speak. Okay, so that's one way to explain it. It works fine, and organic chemists default to this all the time. We call that inductive effects. But the actual explanation has to do with molecular orbital theory, which is just, as I say in the note there, the bullet, it's just beyond the scope of this course. Okay, it's more of a graduate level course thing to understand how molecular orbital theory explains the stability of carbocations. But as I said, for the purpose of this course, because it actually works, is the idea of inductive effects and how those alkyl groups serve as electron donating groups. When I remember, one of the things I remember most from when I had organic chemistry, again, back when dinosaurs roamed the earth, but there was my instructor saying that all the time. So electron is the group electron donating or electron withdrawing, because that explains so much in organic chemistry. So it explains this, because with all these electron donating groups, it sort of tones down that positive charge in the middle with all their own electron density. Okay. Now, some evidence that this is true is from rearrangements that occur to produce more stable carbocations. So there are carbocation rearrangements. So what do we mean by that? Well, those are when carbocations undergo structural rearrangements during that reaction of a halo acid with an alkene. And it can happen in 2 different ways. One is what we call a hydride shift. And so that's when the rearrangement involves a hydrogen atom. So it's a shift of a hydrogen atom and its electron pair between neighboring carbons. And of course, the purpose is to create a more stable carbocation. That's the goal. So if you look at this situation here, that's in the diagram. So again, the pi bond serves as a nucleophile, grabs that hydrogen, okay, and it's going to put it on the most substituted carbon, which is the one in the middle. So if you're following, let me get my pen going here. If you're following, this hydrogen ends up here, okay, because that creates the most substituted carbocation. But that's a secondary carbocation. If you see that carbon's connected to 2 other carbons, that's secondary, right? But right here is a potential tertiary carbocation. All I need to do to get that tertiary carbocation is to move that hydrogen over, right? And so that's what happens. It is an equilibrium process. It's a reversible reaction, but it favors, as you can see with the larger arrow pointing to the right, it favors the tertiary carbocation. So we move the hydrogen over. So now it's moved over to that middle carbon. And now I've got a tertiary carbocation. And so you end up with a mixture of products. Both of these would be in the product mixture, but it would favor the one where the chlorine is on that terminal, or pardon me, that tertiary carbon, okay, because that's the more stable carbocation. All right, so we call that a hydride shift. All right, well, it not only happens with hydrogens, it also happens with alkyl groups. We call that an alkyl shift. So an alkyl shift can occur as well. So the same scenario, right? We've got this alkene. In this case, though, the thing that's different is in the previous slide, this was a hydrogen. Now it's a methyl group, okay? But the same thing can happen. So this alkene reacts with this HCl, okay, adds the hydrogen to the least substituted to create the most substituted carbocation. But wait, that's a secondary carbocation. Well, I'm looking, you know, at a tertiary carbocation right there. If I can move one of these methyl groups over, and so that's what happens. This methyl group moves over, and you get this now a tertiary carbocation, okay, which is more stable. So once again, it's not a 100% process. It's a reversible reaction. It's just that it favors the formation of that tertiary carbocation. And once again, that just affects which chlorine or which carbon the chlorine gets attached to for the final products. And once again, you'll get a mixture. You won't get pure one or the other, but most of the product would be from the more stable tertiary carbocation. We call that an alkyl shift. Okay, so we'll do an example here. So on treatment with hydrobromic acid, HBr, vinyl cyclohexane, which is right there, undergoes addition and rearrangement to yield 1-bromo, 1-ethyl cyclohexane. Using curved arrows, propose a mechanism to account for this result. All right, so let's just try it. We'll try and see what we can do here. Change colors a little bit. Okay, so this hydrogen bromine, there's a single bond there. I'll draw that there. So this nucleophile is going to attack the hydrogen because it's got the partial positive charge. The bromine has a partial negative charge. So that bond is going to go to the bromine to make the bromide. Okay. But then the question becomes, well, which one of these carbons does the hydrogen get added to? The hydrogen gets added to the least substituted. Okay, so I'm going to kind of redraw this here. So I've got the cyclohexane ring. Okay, and so it gets added to the least substituted, which that's the one on the end. So that's going to be a carbon, hydrogen, and then the added hydrogen gets on there as well. And so that's going to have the carbocation ends up on that middle carbon there. Okay, well, remember that there's also a hydrogen here. Okay, it's not shown because this is a skeletal structure and hydrogens are just implied. So what happens is this hydrogen can move, this hydrogen that's here moves over, and that will give us a tertiary carbocation. Okay, so then the product becomes cyclohexane ring. Okay, so now this becomes a CHH with the CH3, CHH, and now the carbocation is right there, and that is a stable tertiary carbocation. So there was that hydride shift, that rearrangement, and so now that's when, you know, the bromide, remember, it's floating around out there. So now it's going to serve as the nucleophile, and it's going to attack the electrophile right there to give us that final bond right there. Okay, so this just shows it prettier.